Right now, this week, Earth is flying through a comet's debris field, and you cannot see it happening. The debris comes from the direction of the sun. The last time an object from this stream detonated in the atmosphere, it flattened 80 million trees across an area larger than London. That was Tunguska, 1908, and the seismometers Apollo astronauts left on the moon recorded a tenfold spike in impacts the last time the densest part of this stream passed close to Earth. The scientist who published those findings last year said 5 words I have not been able to stop thinking about. We had better check. If the fact that Earth is flying through a comet's debris field right now, this week, got you locked in, take a second and hit subscribe to Orbital View. We're tracking the Taurid Resonant Swarm investigation as the observation windows open. Drop a comment with your location if you've spotted any early season fireballs. I read every one. A dead comet skeleton scattered across 100 million miles of inner solar system, and the largest planet in that system acting as a shepherd, herding the most dangerous fragments into a corridor Earth crosses twice a year. The instrument that could finally answer the question, a telescope in Chile that just found 11,000 new asteroids in its first real data release, and a 6-year countdown to the closest encounter in more than half a century. Let's get into it. Part 1, the comet nobody watches. Right now, and I mean this week, the first week of June 2026, Earth is entering a stream of cometary debris that most people have never heard of. The beta Taurids became active on June 5th. They will stay active through July 18th, and unless you are operating a radar array or a radio telescope, you will not see a single one of them. That is the first thing I need you to understand about this story. The Taurid complex hits Earth twice a year. In October and November, the debris arrives on the night side. You can watch it. Fireballs streak across dark skies, slow and bright and sometimes jaw-dropping, turning night into something close to day for a few heartbeats. People film them. They trend on social media. Everybody loves a fireball. But in June, the geometry flips. The debris comes from the direction of the sun. The beta Taurids slam into the daylit hemisphere, and unless something big enough detonates with a flash that outshines the blue sky above you, the whole encounter happens in silence and in blindness. You never know it is happening. The rocks burn up. The atmosphere absorbs the energy. Life goes on. The Tunguska explosion happened on June 30th, 1908, peak of the beta Taurid shower. Same radiant, the same point in the sky the meteors appear to stream from. That date sits inside the beta Taurid window like a bullet hole in a calendar. And the object that detonated over Siberia that morning, roughly 45 meters across, somewhere around 8 megatons of explosive yield, flattened 1,287 square kilometers of taiga forest. 80 million trees, an area larger than the city of London. No crater, no surviving fragments large enough to identify at the time. Just destruction, radiated outward from an airburst at an altitude of 5 to 10 kilometers. The indigenous Evenki reindeer herders who lived in the region described the morning beginning like any other, clear sky, warm for June in Siberia. And then, at approximately 7:14 in the morning, local time, a column of blue-white light appeared in the sky, moving from the southeast. Eyewitnesses more than 500 kilometers away saw the flash. People nearly 650 kilometers away felt the shockwave. And the seismic signal, registered by instruments across Europe, was equivalent to a 5.0 earthquake. For several nights afterward, the sky over Europe glowed. Strange, luminous clouds, noctilucent clouds, formed by water vapor and fine particulate matter injected into the mesosphere, reflected sunlight long after sunset. People in London could read newspapers at midnight by the light of the disturbed atmosphere. If that object had arrived 4 to 5 hours later, Earth's rotation would have placed St. Petersburg, a city of over 1 million people in 1908, directly under the blast. Now, Mark Boslow at the University of New Mexico published a paper in Acta Astronautica last September. The proceedings of the 9th Planetary Defense Conference in Cape Town, South Africa. The paper is titled 2032 and 2036 Risk Enhancement from NEOs in the Taurid Stream. The co-authors include Peter Brown, David Clark and Paul Wiegert at Western University in Canada, and Quanji Ye, one of the leading meteor physicists in the field. And Boslow specifically called for observations in June 2026. This month, he wants telescopes pointed at this part of the sky because the hypothetical Taurid Resonant Swarm, a dense cluster of debris that Jupiter's gravity may be hurting through the inner solar system. Chekomals is making one of its periodic approaches. This is not the closest approach. 2032 will be closer. 2036 will be closer still. But 2026 is a preliminary window, see, a chance to start characterizing the swarm's large body population before the critical encounter years arrive. And with the Vera C. Rubin Observatory, now operational in Chile, a telescope with the largest digital camera ever built in astronomy, capable of scanning enormous swaths of sky and detecting objects too faint for any previous survey. The June 2026 window is the first time we have ever had both a reasonably close swarm approach and an instrument sensitive enough to find what might be hiding in it. The convergence of timing and capability is not lost on the planetary defense community, but I want to convey something that I think matters beyond the scientific specifics. This month, right now, is an inflection point, not because an impact is imminent, it is not, but because the question of what is in the Taurid Resonant Swarm has been theoretical for 30 years. And starting this summer, for the first time, it can become empirical. I want to be careful here, and I will be throughout this entire investigation. Boslow himself says the average probability of a dangerous impact is extremely low. Even an enhanced risk, he says, means the probability would still be low. But he also says something else that I think carries more weight than the reassurance. He says, and I want to get this exactly right, from a risk assessment perspective, we had better check. And that tension between the probability is low and we had better check is what this entire video is about. Because the reason we had better check is not academic curiosity. It is not the general principle that knowing more is better than knowing less, although that is true. It is that the entire framework we use to calculate impact risk assumes those impacts arrive randomly, spread out, uncorrelated, one at a time from any direction without pattern or preference. And the Taurid Resonant Swarm, if it exists in the way the evidence suggests, violates that assumption. Not slightly, not at the margins, structurally. The models that tell us how safe we are, the models that Congress funds, that NASA reports on, that international agencies coordinate around, assume that the probability of a city-killing airburst is the same in any given week as in any other week, in any given year as in any other year. But if debris is concentrated by Jupiter's gravity into a corridor that Earth crosses on a schedule, then some weeks are riskier than others. Some years are riskier than others, and the models do not account for that. They were not built to account for that, and nobody has tested whether they need to be. That is the thesis. The models say random. The debris says clustered, and we are about to find out which one is right. Part 2. What came through the atmosphere? I want to take you to the morning of February 15th, 2013. Chelyabinsk, Russia. A city of about 1 million people in the southern Urals. 9:20 in the morning, local time. Kids are walking into classrooms. Commuters are on the road. The temperature is well below freezing. Normal for February in that part of the world. Nobody is looking at the sky, and the sky is about to break open. At 9:20 and 28 seconds, a rock about 20 meters across, 66 feet, roughly the size of a 6-story building, entered Earth's atmosphere, traveling at 12 miles per second. 19 kilometers per second if you want the metric. It had approached Earth from the sunward side, the most dangerous approach geometry in planetary defense, because ground-based telescopes cannot see objects that are silhouetted against the glare of the sun. No telescope detected it, no survey flagged it, no early warning system registered its existence. The entire global network of asteroid hunting telescopes, Kiki, Arik, Kraki, Enfor, Catalina, Pan-STARRS, the precursor surveys, missed it completely. Not because they failed, because the object came from the one direction they cannot see. The object arrived without introduction, without warning, and without any of the institutional machinery that is supposed to protect cities from exactly this kind of event, having the slightest idea it was coming. The first thing people noticed was the light, dashcam footage, and there is a staggering amount of dashcam footage from Russia, shows a white hot streak cutting across a gray winter sky. Eyewitnesses compared the brightness to the sun, and they were not exaggerating. Measurements later confirmed that the flash was, briefly, brighter than the sun as seen from the ground. More than 180 people reported eye pain in the hours that followed. 20 people suffered ultraviolet burns, essentially sunburn from a rock, possibly intensified by the reflection off snow cover. The asteroid did not hit the ground. It detonated in the atmosphere at an altitude of roughly 18.5 miles. An airburst, and the energy it released was estimated at 500 kilotons of TNT. The Planetary Society puts it at 500 kilotons. Lawrence Livermore National Laboratory, which ran high-fidelity simulations of the event years later, confirmed the figure. The bomb dropped on Hiroshima yielded roughly 15 kilotons. Chelyabinsk was more than 30 times that. A rock the size of a modest apartment building, moving so fast the atmosphere could not get out of its way, converting its entire kinetic energy into an explosion in the sky above a city of 1 million people. The shockwave hit the ground minutes after the flash. Think about that gap. The flash is instantaneous. Light travels at the speed of light. The shockwave is a pressure wave in air, moving at roughly the speed of sound. So people saw the flash, stared at the trail in the sky, maybe started reaching for their phones, and then the blast wave arrived. Windows exploded inward. Doors blew off hinges. A factory roof collapsed. Car alarms screamed across the city. And glass, an enormous volume of broken glass, became shrapnel. More than 7,200 buildings across 6 cities were damaged. 1,500 people sought medical treatment, almost all of them cut by flying glass. Vladimir Basmanikov, a surgeon at a Chelyabinsk hospital, described the scene. We have treated people mainly with incised and contused wounds, all due to shattered windows and broken window frames. Look how many people we have here. We have already treated 60 or 70 people, and we still have a corridor full of people. The governor of Chelyabinsk Oblast, Mikhail Yurovich, estimated the damage at more than 1 billion rubles, roughly $30 million, and the government scrambled to repair more than 100,000 homes worth of windows before the sub-zero temperatures turned a blast event into a hypothermia crisis. And here's a detail that makes this story stranger, and that I think most people have forgotten. On the exact same day, February 15th, 2013, the asteroid 2012, DA-14, made its closest approach to Earth, passing inside the orbits of geostationary communications satellites. 17,200 miles from the surface, the entire astronomical community was watching DA-14. Television crews were set up, press conferences were scheduled, and while every telescope on the planet was pointed at the asteroid they knew about, a completely different rock came in from the direction of the sun and exploded over a Russian city. The two events were unrelated. Different trajectories, different origins, pure coincidence. But the timing underscored something that the planetary defense community already knew, and that Chelyabinsk drove home with shattered glass and hospital corridors. The objects that hurt you are the ones you do not see coming. And that brings me to the counterfactual that I think is the most important thing about Chelyabinsk, more important than the damage figures, more important than the shockwave physics, more important than the dashcam footage. Scientists calculated that if the Chelyabinsk object had arrived 4 to 5 hours later, Earth's rotation would have placed a different city under the blast. If it had arrived at a steeper entry angle, or if the object had been slightly more structurally coherent, the burst altitude would have been lower, closer to the surface, and the shock wave would have been proportionally more devastating. A 500 kiloton airburst at 5 kilometers altitude instead of 18.5 would produce overpressures at the surface capable of collapsing buildings, not just breaking their windows. The difference between 1,000 injuries and 10,000 casualties is not object size. It is burst altitude and population density. Chelyabinsk was, by any honest assessment, a near miss dressed up as a minor disaster. The object was small enough to detonate high. The city was spread out enough to absorb the shockwave. The timing was unlucky enough to hit a populated area, but lucky enough to hit it from the right altitude. Change any one of those variables, and the story is different, darker. And here is what I keep coming back to. This was a 20-meter object, Chelyabinsk class, the largest natural object to enter Earth's atmosphere since the Tunguska event in 1908. That is a gap of 105 years between the two biggest atmospheric detonations in modern history. But the question this investigation is really asking is not about how often random impacts occur. It is about whether certain impacts are not random at all, whether they are concentrated, whether the debris that produced Chelyabinsk-scale events could be clustered in a specific region of the solar system that Earth passes through on a schedule. Because if that is true, if those objects are clumped, not scattered, then the probability calculations that underpin every planetary defense assessment on Earth need to be revisited, not next decade, now. Part 3, the river of debris. So where does all this debris come from? And why is there so much of it? The answer starts with a comet that most people will never hear about, and that astronomers have known about for more than 2 centuries. Comet 2P/Encke, usually just called Comet Encke. First observed in 1786, formally identified and named after the mathematician Johann Franz Encke, who computed its orbit in 1819 and realized that multiple comet sightings were the same object returning again and again. It has the shortest orbital period of any known comet, 3.3 years. Every 3.3 years, it loops around the sun, and every time it does, it sheds material, dust, gravel, fragments of ice and rock boiling off under solar radiation. Its nucleus is small by cometary standards, roughly 4.8 kilometers across, about 3 miles cest and shrinking with every passage. Each perihelion passage strips away a little more of the surface, exposing fresh ice to the furnace of solar radiation, releasing gas and dust that gets swept into the comet's tail, and then gradually spreads along the orbital path. The material Encke has shed over millennia forms the visible Taurid meteor showers. But the visible showers, the southern Taurids in October and November, the northern Taurids slightly later, the beta Taurids in June, are only the surface expression of a much larger structure. Fred Whipple, the astronomer who developed the modern model of comets as dirty snowballs, first proposed in 1967 that Encke was the main source not just of the Taurid showers, but of a significant fraction of the zodiacal cloud, the faint band of interplanetary dust that glows along the ecliptic in dark skies. If that connection is real, the debris from Encke and its relatives is not just a meteor shower. It is a pervasive feature of the inner solar system. But Encke itself is not the whole story. Not even close. And this is the part where the scale of what we are dealing with starts to come into focus. Think of a frozen lake, a lake so large you cannot see across it, surface area the size of a county. Now imagine that lake shattering, not all at once, but over millennia, cracking and breaking into fragments that range from ice dust to icebergs the size of office buildings. The dust spreads quickly, it gets picked up by currents, scattered across the surface, but the bigger pieces drift more slowly. They jostle, they collide, they shed their own fragments, and some of those pieces are big enough to punch through the hull of any ship that hits them. That is the Taurid complex. And the lake, the original frozen body, was a comet that makes Encke look like a snowball. In 1984, 2 British astronomers, Victor Clube, an astrophysicist at the University of Oxford, and William Napier at the Royal Observatory, Edinburgh, proposed what is now called the giant comet hypothesis. Their argument was that Comet Encke is not the source of the Taurid complex. Encke is a survivor, a leftover, a chunk. The real source was a comet on the order of 100 kilometers across, 62 miles wide, comparable to a typical Kuiper Belt object, something like Hale-Bopp's larger, meaner cousin, that entered the inner solar system between 10,000 and 30,000 years ago. and as it orbited the Sun on a roughly 3.3-year period, solar heating and internal stress began to tear it apart. The breakup was not a single event. It was a process, a slow-motion catastrophe playing out over thousands of years, invisible to any species that might have been watching from the ground below. Daughter comets calving off the main body as thermal stress fractured the surface. Rocky cores exposed as overlying ice sublimated away under the relentless bombardment of solar radiation. Collisions between fragments producing secondary debris, a cascade of fragmentation feeding itself, each generation of breakup producing smaller pieces that were more vulnerable to further disruption. Boulders the size of houses, rubble fields the size of neighborhoods, gravel, dust, all of it spreading along the orbital path, some of it drifting outward under the gentle pressure of sunlight, some of it staying close to the parent body's trajectory, accumulating into a debris stream that broadened and thickened over millennia until it became the structure we see today. And the structure we see today is enormous. A vast, diffuse tube of material crossing Earth's orbit, wide enough to take weeks to traverse, extending across a significant arc of the inner solar system. The total mass of the Taurid complex, all the dust, all the meteoroids, all the asteroids, all the fragments, has been estimated by some researchers to rival or exceed the mass of Comet Encke itself, which means the progenitor object was far larger than anything currently visible in the stream, which is exactly what the Clube-Napier hypothesis predicts. For decades, the Clube-Napier hypothesis sat at the edge of mainstream acceptance. Intriguing but unproven. Suggestive but circumstantial. Some astronomers embraced it, others dismissed it as overreach, noting that the diversity of asteroid compositions in the proposed complex was hard to reconcile with a single cometary parent. And the hypothesis carried political baggage. Clube and Napier had also proposed that fragments of the Taurid complex had influenced human civilization through periodic bombardment, an idea that strayed into territory some colleagues found uncomfortably speculative. But the observational evidence kept arriving from unexpected directions. In 1962 and 63, the Soviet Mars 1 probe, Tsu, en route to Mars, recorded micrometeorite strikes at a rate of 1 every 2 minutes as it passed through the Taurid meteor stream at altitudes between 6,000 and 40,000 kilometers above Earth's surface. Similar impact densities were recorded at distances of 20 to 40 million kilometers from Earth. The stream was not a thin, diffuse mist. It was a broad, populated structure with measurable density extending far from Earth. And then, starting in the 2000s, the evidence started stacking in a way that shifted the center of gravity in the debate. In 2020, Ignacio Ferrin at the University of Antioquia in Medellin, Colombia, and Vincenzo Orofino at the University of Salento in Italy published a paper that reanalyzed more than a dozen studies from the decades since Clube and Napier's original proposal. They used a technique called secular light curves, tracking changes in each object's brightness along its orbit to look for signs of cometary activity. Active comets brighten as they approach the Sun because solar heating causes ices to sublimate and produce a coma, a fuzzy envelope of gas and dust. Dead comets do not brighten. Rocky asteroids do not brighten. Only objects with surviving volatile ices show this signature. Ferrin and Orofino identified 88 probable members of the Taurid complex, asteroids and cometary fragments whose orbits share a common lineage with Encke and with each other. Of the 51 members they had good enough data on to analyze, 67% showed evidence of cometary activity. Not dead, inert rocks. Active bodies, still outgassing, still shedding material, still behaving like pieces of a comet that broke apart relatively recently in geological terms. Some of these objects are more than a mile across. They are far too large to have come from Encke directly. Encke's nucleus is only about 3 miles in diameter. The implication is exactly what Clube and Napier proposed 40 years earlier. A massive progenitor comet broke apart, and Earth's orbit passes through the wreckage field twice a year. Every year. On schedule. But here is where the story turns from interesting to genuinely concerning. Because the wreckage is not evenly distributed, Part 4. The resonance trap I need to explain a piece of orbital mechanics that sits at the center of this entire investigation. And I am going to explain the concept before I name it, because the concept matters more than the vocabulary. Jupiter is enormous. It is the most massive planet in the solar system by a factor that is hard to overstate. More than twice the mass of every other planet combined. 318 times the mass of Earth. Its gravitational influence extends far beyond its own orbit, and when smaller objects, asteroids, cometary fragments, meteoroids, orbit the Sun in a pattern that brings them close to Jupiter at regular intervals, Jupiter's gravity does something remarkable. It does not just tug on them randomly. It corrals them. Think of a sheepdog working a flock on a hillside. The dog does not chase individual sheep. It positions itself, over and over, at the same angle, the same distance, applying the same pressure. And over time, the flock clusters. It tightens. It stays together not because the sheep want to be together, but because the dog keeps nudging them into the same patch of ground. Jupiter is the dog. The debris in the Taurid stream is the flock. And the specific pattern that creates the shepherding is what astronomers call a mean motion resonance. Specifically, a 7-to-2 resonance. Objects that orbit the Sun 7 times for every 2 orbits of Jupiter complete their paths in a ratio that brings them back to the same relative position with respect to Jupiter at regular intervals. And at each of those encounters, Jupiter's gravity gives them a small nudge. Over a single orbit, the nudge is negligible. Over 100 orbits, it starts to matter. Over 1,000 orbits, a few thousand years, for objects with Taurid-like periods, the accumulated nudges sort the debris. Objects near the resonance get pushed toward it. Objects at the resonance stay there. The result, over millennia, is a concentration, a filament of material that is denser than the surrounding stream. This is not exotic physics. It is the same mechanism that creates the Kirkwood gaps in the asteroid belt, regions where Jupiter's resonances have cleared material away, and the narrow ringlets in Saturn's ring system, where tiny shepherd moons concentrate ring particles into tight, well-defined bands. The mechanism is well understood, mathematically described, and observationally confirmed across the solar system. The question is not whether it can work in the Taurid stream. It is whether the Taurid stream contains enough large material for the concentration to matter. David Asher, a dynamicist at Armagh Observatory in Northern Ireland, and Victor Klube first described this mechanism mathematically in 1993. They predicted that the resonant swarm would produce enhanced Taurid activity, more fireballs, brighter fireballs, larger meteoroids than in non-swarm years. In specific years, when Earth's orbit brings it close to the swarm's densest region, and they made predictions. Specific years: 1995, 1998, 2005, 2008. Enhanced Taurid activity was observed in every single one of those predicted years. The European Fireball Network documented elevated fireball rates in 1995 and noted that 5 fireballs observed during the last week of October that year had distinct but remarkably similar orbits. Tighter clustering than the regular southern Taurids. Visual observations confirmed increases in 1998 and 2005. 2008 and 2015 both produced elevated fireball counts, consistent with the swarm prediction. And 2022 was a swarm year too. Robert Lunsford at the American Meteor Society noted that fireball activity in October 2022 was well above normal, with visual observers and astrophotographers capturing several fireballs per night instead of the normal rate of roughly one every 20 hours. The cyclical reappearance, 2008, 2015, 2022, follows a roughly 7-year period, and each appearance has been accompanied by an increase in the percentage of fireballs among total Taurid meteors. In a typical year, fireballs make up about 1% of all Taurid meteors. In swarm years, that percentage can climb to 7%. 7% does not sound dramatic until you realize what it means in practice. Not one slow golden fireball every 20 hours of patient watching, but several per night, some bright enough to cast shadows and trigger car alarms, some leaving persistent trains of ionized gas that glow against the stars for minutes after the meteor itself has vanished. In 2022, the most recent swarm year before the current cycle, observers across North America, Europe, and Asia reported fireball sightings that exceeded normal rates by a significant margin. Robert Lunsford of the American Meteor Society noted that fireball activity that October was higher than normal, and visual observers and astrophotographers captured multiple bright Taurid fireballs in a single night of watching. The pattern held true to Asher and Klube's predictions yet again, and 2025 was also a swarm-adjacent year. Lunsford noted that Earth was passing through the outer edge of the swarm during the November 2025 southern Taurid peak, and reported that even at the edge, fireball activity in October had been higher than anticipated. The activity cycle is behaving exactly as the resonance model predicts, reliably, repeatedly, over 3 decades of observations. The next predicted swarm encounter is 2032, and that one is different from every encounter before it for reasons that I will lay out in detail later. But first, I need to address what the 2015 data revealed, because 2015 was the year the cameras were ready and the year the investigation crossed from prediction into observation. But I have to be honest about what confirmed means in this context, because this is where the uncertainty lives and where I refuse to paper over it. What was observed were more fireballs than usual, brighter than usual. In the predicted years, that is consistent with the swarm hypothesis. It is not proof, it is consistent. And the distinction between consistent with and proven by is doing a lot of analytical work in this investigation. What would move the needle from consistent to confirmed is direct observation of the larger objects, the Chelyabinsk class and Tunguska class fragments that, if they exist inside the resonant swarm, would represent an actual threat. And that brings us to the data set that changed this entire field. Part 5, the year the cameras caught it. In 2015, Earth passed through the Taurid Resonant Swarm during the predicted window, late October through mid-November. And this time, the European Fireball Network was watching with equipment that had been upgraded specifically for this encounter. New digital autonomous fireball observatories, JACTI instruments designated DAFO, had been deployed across a network of stations spanning the Czech Republic, Slovakia, and Austria. These are not consumer cameras. Each DAFO unit uses a fisheye lens to capture the entire sky in a single frame, with precise timing, calibrated photometry, and the ability to measure the position of a fireball at multiple points along its trajectory from multiple stations simultaneously. Triangulate from 3 or more stations, and you can compute the fireball's 3-dimensional trajectory, its velocity, its deceleration in the atmosphere, and, critically, its heliocentric orbit before it entered Earth's gravitational sphere of influence. This is the difference between seeing a fireball and understanding a fireball. Anyone with a camera can capture a streak of light. The European Fireball Network can tell you where that light came from, which orbit it was following, what its relationship to Jupiter is, and whether it belongs to the same dynamical family as 100 other fireballs observed that month. Pavel Spurny, at the Astronomical Institute of the Czech Academy of Sciences, led the analysis. His team recorded 144 Taurid fireballs during the 2015 enhanced activity window, between October 25th and November 17th. One of the brightest designated EN 051115_231201 was captured by DAFO cameras at 4 stations: Dult, Martinsburg, Kunjak, Kuchajovice, and Chervona Hora, providing a multi-angle dataset precise enough to reconstruct its path through the atmosphere to within a single standard deviation of a few meters across dozens of measured trajectory points. Of the 144 fireballs, 113 shared orbital characteristics so precise, so tightly clustered, that they formed what Spurny called a new branch, a well-defined orbital structure within the southern Taurids that had never been documented at this resolution before. And I want to linger on what well-defined means in this context, because it is doing more work than it might seem. These were not fireballs scattered randomly across the broad Taurid stream. Their orbits formed a concentric ring in the inner solar system. Their semi-major axes, The size of their orbits around the Sun fell between 2.23 and 2.28 astronomical units. Their eccentricities, how elongated the orbits were, ranged from 0.80 to 0.90. And the semi-major axis range overlaps directly with the 7-2 Jupiter resonance that Asher and Klube predicted 22 years earlier. The precision of this clustering is striking even by the standards of meteor science, where orbital families and streams are well-established concepts. The new branch meteoroids did not just loosely share a neighborhood in orbital element space. They occupied a tight, well-bounded region, a fingerprint that is extremely difficult to explain by coincidence and extremely easy to explain by resonant trapping. And Spurney's team was not the only group that saw the enhancement. The Desert Fireball Network in Australia, an independent network with its own cameras and its own data pipeline, observed a significant outburst of fireballs belonging to the Southern Taurid complex between October 27th and November 17th of 2015. The same time window, the same phenomenon, detected independently on the other side of the planet by a completely separate set of instruments. That independent confirmation eliminates the possibility that the 2015 result was an artifact of the European network's calibration or a statistical fluke in a small dataset. This is observational evidence, not theoretical modeling, not statistical inference from sparse data. 113 individually tracked fireballs from one network, corroborated by an independent detection from a second network on a different continent, their orbits computed from multi-station imagery to precisions far beyond what earlier campaigns achieved, confirming that large meteoroids, objects big enough to produce fireballs, visible across hundreds of kilometers, are being concentrated by Jupiter's gravity into exactly the orbital corridor that theory predicted. The paper was published in Astronomy and Astrophysics in 2017, and its title includes the phrase, "a real source of potentially hazardous bodies." I want you to sit with that phrasing for a moment. Pavel Spurney, a career meteor physicist, a man who has spent decades tracking fireballs across the European sky, did not title his paper "An Interesting Dynamical Phenomenon" or "A Statistical Anomaly in Meteoroid Orbits." He titled it "A Real Source of Potentially Hazardous Bodies." But the paper contained something beyond the fireball statistics, something that moved the investigation from an astronomical curiosity to a planetary defense question. 2 near-Earth asteroids, BTU designated 2015, TX-24 and 2005 UROs, were found to have orbits that placed them squarely inside the resonant branch. These are not dust grains. These are not pebbles, not even meteoroids. These are objects several hundred meters in diameter, batalos in football field scale rocks, orbiting in the same gravitational trap that concentrates the fireballs. And the 2025 Bouslow paper reinforced this finding. It noted that the overall behavior of the Taurid Resonant Swarm and its apparent linkage with large meteoroids has been recently demonstrated through the 2015 high-precision fireball measurements, confirming with high precision the 7-2 mean motion resonance with Jupiter and showing that large meteoroids can be shepherded and concentrated by the resonance. Shepherded and concentrated. Those are the words. Not scattered, not diffuse, not randomly distributed, shepherded and concentrated. So the question is no longer whether the resonance works at the meteoroid scale. The 2015 data settles that. The question is, what else is being shepherded? What is hiding in that concentrated corridor that we have not seen yet because we were not looking with the right instruments, or because the objects are too dark, or because they approach from the direction of the sun? That question has an answer. We just do not have it yet, but the instruments that could provide it are now online, and the clock is running. Part 6, What the Moon Remembers. And this is where the story takes a turn that most coverage completely misses, because the evidence for the Taurid Resonant Swarm does not come only from fireball cameras pointed at the sky. Some of it comes from seismometers left on the surface of the moon by Apollo astronauts more than 50 years ago. And the data those instruments recorded is, in my view, among the most underappreciated pieces of evidence in all of planetary science. Between 1969 and 1977, NASA's Apollo passive seismic experiment recorded over 12,000 seismic events on the lunar surface. 4 stations deployed during Apollo 12, 14, 15, and 16 would operated for nearly 8 years. The instruments were remarkably sensitive for their era, and the data set they produced remains one of the most valuable long-duration seismic records ever collected anywhere beyond Earth. They picked up deep moonquakes originating hundreds of kilometers below the surface, shallow moonquakes from tectonic stress, thermal quakes caused by temperature changes as the lunar day-night cycle cycled the surface through swings of nearly 300 degrees Celsius, artificial impacts from intentionally crashed Saturn V rocket stages, and lunar modules that NASA used to calibrate the network, and meteoroid strikes. Every time a piece of debris hit the moon hard enough to shake the ground, the seismometers registered a signal. And from that signal, its amplitude, frequency content, and arrival time at multiple stations, scientists could estimate the mass, velocity, and energy of the impactor. The moon is a remarkably good seismic detector for meteoroid impacts, and the reason is counterintuitive. On Earth, seismic signals from distant events are quickly damped by the geologically active, water-saturated, structurally complex crust and mantle. Seismic energy gets absorbed. Events fade fast. On the moon, the opposite is true. The lunar crust is bone dry, intensely fractured from billions of years of impacts, and extremely efficient at scattering seismic energy rather than absorbing it. Even a small impact can ring the moon like a bell, the seismic signal reverberating for an hour or more, sometimes several hours, bouncing and rebouncing through the shattered megaregolith. The largest recorded meteoroid impact on the moon produced a signal that lasted 5 hours. This scattering is a nightmare for seismologists trying to identify clean reflected and refracted phases for interior structure studies. But it means that impacts which would vanish in the noise on Earth are clearly registered on the moon. Now here's the piece I need you to lock onto. In 1975, the daytime Taurid Resonant Swarm, the beta Taurids, the June shower that you cannot see because it comes from the direction of the sun, made a close approach to Earth's vicinity, and during that encounter, the Apollo seismometers on the lunar surface recorded a 10-fold increase in the meteoroid impact rate. A 10-fold increase, not 10% more impacts, not double. 10 times the normal rate. Boslow cites this in his 2025 paper. The 1975 daytime Taurid Resonant Swarm, he writes, has been associated with an order of magnitude increase in the impact rate on the moon as measured by Apollo-era seismometers. And this matters immensely because it is not modeling, it is not prediction, it is not optical observations through an atmosphere that introduces noise and uncertainty. It is seismic data, vibrations in rock, recorded by instruments that astronauts physically carried to the lunar surface and set down with their own hands. The moon got hit more, a lot more, during exactly the window the swarm theory predicted. And the beauty of this evidence, the reason I keep returning to it, is its independence from every other line of evidence in this investigation. The fireball data comes from optical cameras. The orbital analysis comes from dynamical modeling. The swarm predictions come from resonance theory. The lunar seismic data comes from a completely separate physical measurement on a completely separate body. It is not possible to gerrymander this evidence to fit the hypothesis. Either the moon experienced an anomalous spike in meteoroid impacts during the predicted swarm encounter window, or it did not. The seismometers say it did. Tenfold. Now, I need to be fair to the uncertainty. The Apollo seismic network was small, 4 stations on the near side of the moon, covering a limited area. The catalog of meteoroid impacts was compiled from long-period seismometer data and distinguishing meteoroid impacts from other seismic sources. Shallow moonquakes, thermal events, required classification judgments that carry some ambiguity. Recent reanalysis by Karin Onodera in 2024 discovered more than 22,000 uncatalogued moonquakes in the Apollo short-period seismic data that had gone unexamined for decades, suggesting that the original catalogs were incomplete. The 1975 impact spike is real in the data, but the degree to which it can be attributed exclusively to the Taurid swarm versus other meteoroid populations active at the same time has not been fully resolved. That said, the timing correlation is precise. The spike occurs during the predicted beta Taurid swarm window, and no comparable spike has been identified during non-swarm periods in the Apollo dataset. The evidence is not conclusive proof of the swarm hypothesis, but it is strong, independent, and directional. That was 1975, the last time the hypothetical swarm made a close daytime approach. The Apollo seismometers were shut down in 1977, so there is no comparable seismic data from subsequent encounters. And the next close approach at that daytime geometry will not come until June 2036. But here's the problem with 2036 that makes the 2032 window so critical, and that I will return to in detail later. In 2036, the swarm approaches from the direction of the Sun. Objects in it are invisible to ground-based optical telescopes until they pass Earth and recede into the night sky, or until one of them enters the atmosphere. Boslow is blunt about this. Fireballs will not be seen in our blue skies, he says, unless they are extremely bright. So the cleanest observational window, the one where we can actually see what is in the swarm, is November 2032. The night side encounter? Dark skies. And as it happens, the moon will be new during the peak of the Taurid activity window that month. No moonlight interference. Optimal conditions. Hold that timeline. 6 years. Because everything that follows in this investigation connects back to it. Part 7, the asteroids hiding in the stream. Let me step back for a moment and describe what we are actually talking about when we say the Taurid complex, because I think most people have not fully absorbed the scale of this structure. Picture the inner solar system, everything inside the orbit of Jupiter. Now imagine laying a vast diffuse ring of debris along a slightly tilted, slightly elliptical path that crosses Earth's orbit twice. This ring is not a thin line, it is a broad tube of material, millions of miles across at its widest, containing everything from particles smaller than a grain of sand to objects several hundred meters in diameter. The ring has structure, denser regions and sparser regions, like a river with deep channels and shallow banks. And Earth plows through this river every year, twice a year, as predictably as a commuter crossing the same bridge on the way to work. Within that ring, the 7-2 resonance with Jupiter creates a substructure, a denser channel, a concentrated filament. That is the resonant swarm. And the question that Boslow's paper, Spurney's observations, and 30 years of theoretical work all converge on is, how big do the objects inside that filament get? Dust and pebbles are a certainty. We see them every year as meteors. Meteoroids, large enough to produce bright fireballs, objects ranging from a few inches to a few feet across, are confirmed by the 2015 European Fireball Network campaign. 113 of them tracked in a single season. But beyond that size range, things get murkier. And I am going to walk through the evidence carefully because the uncertainty here deserves precision, not hand-waving. The two near-Earth asteroids I mentioned, 2015 TX-24 and 2005 UR8, have orbits that place them inside the resonant branch. These are bodies several hundred meters in diameter. Their presence inside the swarm's orbital space is established by mathematical analysis of their trajectories. The distinction that matters, and that I want to be transparent about, is between orbital association and genetic relationship. An object can share orbital elements with the swarm without being a physical fragment of the same progenitor comet. Orbital space is vast, but it is not infinite. Sometimes unrelated objects end up in similar orbits through coincidence or through separate gravitational interactions with Jupiter. Spectral evidence is mixed. Popescu and colleagues in 2014 examined 6 large asteroids proposed as members of the Taurid complex and found that 5 of them had surface compositions inconsistent with cometary origin. They looked like ordinary rocky asteroids from the main belt, not fragments of an icy comet. That finding weakened the case for those specific objects being Taurid siblings, though it did not rule out the broader hypothesis since cometary fragments can be coated in dark, carbonaceous material that masks their original composition after thousands of years of solar processing. The surface you see today may bear no resemblance to the interior. Farine and Orofino's 2020 work pushed the pendulum back. Their secular light curve analysis found 67% of Taurid complex candidates showing cometary activity. That is a remarkably high percentage for a population that most surveys had assumed was dominated by dead, inactive objects. And Farine, whose earlier work had tracked the Chelyabinsk meteor and contributed to understanding its origin, specifically identified the asteroid Hephaistos and the Comet 169 P/NEAT as active members of the complex with their own subgroups of associated debris. Hephaistos deserves a moment of attention here because it is one of the larger objects in the proposed Taurid complex, and it illustrates the scale of what the giant comet hypothesis implies. Hephaistos is roughly 5.5 kilometers in diameter, more than 3 miles across. It orbits the Sun on a highly elliptical path that crosses the orbits of both Earth and Mars. If Hephaistos is genuinely a fragment of the Taurid progenitor, and the orbital and activity evidence from Farine and Orofino suggests it may be, then the breakup of the original comet produced not just meteoroids and fireballs, but multi-kilometer objects capable of catastrophic impact. Hephaistos itself is not on a collision course with Earth in the foreseeable future, but its existence inside the complex raises the question of what other large fragments may be out there, fragments that have not yet been discovered because they are darker, smaller, or on orbits that existing surveys have not adequately covered. So what is the actual population of dangerous-sized objects in the swarm? Quanzi Ye, one of Boslow's co-authors and a researcher who presented findings at the 9th Planetary Defense Conference in Cape Town, attempted to estimate this. Using the observed density of fireballs in the resonant branch and extrapolating upward to larger sizes, Ye estimated the swarm might contain roughly 1,000 Chelyabinsk-sized objects. Objects around 20 meters in diameter. The size class that if one strikes a populated area produces the kind of damage we saw in February 2013. But Ye attached a caveat that I think is the single most important qualifier in the entire investigation supporting literature. The estimate, he wrote, is based on the unverified assumption that the orbital distribution of the larger objects follows that of the observed fireballs and meteors. And he explicitly noted that larger bodies experience noticeably different dynamical processes compared to sub-meter-sized meteoroids. Radiation pressure, Yarkovsky effect, collisional evolution, the physics that governs a grain of sand in Jupiter's gravitational field is not the same physics that governs a 100-meter boulder. So the number Tauride, 1,000 Chelyabinsk-class objects, gas, is not a finding. It is a scenario that, even if correct, translates to an impact frequency of less than once every 4 million years. That is a reassuring number. If it is right, is carrying the weight of every untested assumption underneath it. And the whole point of Boslow's paper is that those assumptions have not been tested with the instruments and during the windows that would actually constrain them. Part 8, the blind spot in planetary defense. I have spent a lot of time watching how the international community assesses impact risk, and the architecture that has been built over the past 3 decades is genuinely impressive. The Catalina Sky Survey, operating out of the University of Arizona's Steward Observatory on Mount Lemmon, has been one of the most prolific asteroid discovery programs in history. Pan-STARRS in Hawaii, with its wide field survey capability, scans the sky systematically. The Atlas telescopes, the asteroid terrestrial impact. Last Alert System, funded by NASA and operated by the University of Hawaii, were designed specifically for short warning time detections, with the explicit goal of finding impactors in the days or weeks before they arrive. The Space Surveillance Network tracks objects in Earth orbit, and internationally, the European Space Agency's Near-Earth Object Coordination Center in Frascati, Italy, coordinates observations across a network of telescopes. These systems have collectively discovered more than 35,000 near-Earth objects. The congressional mandate, GIS, the George E. Brown Act from 2005, directed NASA to find 90% of all near-Earth asteroids larger than 140 meters. That effort is serious, well-funded, and ongoing. The DART mission in September 2022 proved that humanity can deflect an asteroid by kinetic impact. The Dimorphos moonlet's orbit was shortened by more than 30 minutes, far exceeding predictions. The whole system is designed, funded, and operated on a foundational assumption that threats arrive one at a time from random directions on trajectories we can calculate years in advance. For most of the near-Earth population, that assumption is correct. Asteroids perturbed out of the main belt by gravitational interactions with Jupiter and Saturn do arrive on essentially random, uncorrelated orbits. Finding them, tracking them, predicting their future encounters with Earth, these are problems of survey completeness. See enough of the sky, often enough, with sensitive enough instruments, and you will find them. But the Taurid Resonant Swarm does not play by those rules. And the compound connection I need to make explicit here is the one that ties every thread of this investigation into a single knot. Consider how the surveys work. A telescope images a patch of sky. Software identifies objects that move against the fixed background of stars. The motion is measured over multiple nights. An orbit is computed. The orbit is projected forward. And the question is asked, does this orbit bring the object close to Earth at any point in the next century? That process works brilliantly for isolated objects on well-determined orbits. It does not work for a swarm of small dark objects embedded in a meteor stream. The objects are faint, potentially fainter than the detection limits of existing surveys, especially if they are low albedo cometary fragments. They are numerous, potentially thousands of Chelyabinsk-class objects in a concentrated filament, each one individually below the size threshold that surveys prioritize. And they arrive from a predictable direction during predictable windows, which means the survey strategy could, in principle, be optimized for them, but currently is not. If impact risk has a coherent component, if debris is clustered in space and time, not scattered randomly, then the way we calculate risk needs structural revision. The standard method divides the total population of near-Earth objects by time. Over 1 million years, how many impacts of a given size should we expect? Divide that down to a per-year probability. The result is a number to a very small number c that tells you how worried to be. And that calculation works perfectly if impacts are randomly distributed across time. It fails if they are concentrated, and the failure mode is specific and quantifiable. If impacts cluster, the per-year average underestimates the risk during cluster windows and overestimates the risk during non-cluster periods. The average might be correct in a mathematical sense. Over millions of years, the right total number of impacts occurs. But the distribution is wrong, and civil defense does not operate on million-year averages. Civil defense operates on weekly and monthly timescales. In a 3-week window during a swarm encounter, the risk could be orders of magnitude higher than the annual average implies, and in the 50 other weeks of that year, correspondingly lower. This is not a novel insight in risk science. Insurance companies deal with correlated catastrophic risks constantly. Hurricanes cluster by basin and season. Earthquakes cluster on specific faults and in specific subduction zones. Pandemics cluster by pathogen lineage and transmission route. The entire discipline of catastrophe modeling exists because treating rare events as uniformly distributed in time and space produces systematically wrong risk estimates for the windows and places where concentration exists. Boslow's paper addresses this head-on. There is significant evidence for the existence of a Taurid Resonant Swarm. He writes, which effectively provides an existence proof that risk cannot be assumed to be purely stochastic. And then the sentence that follows, which I think deserves to be read slowly. There is no theoretical or observational evidence that coherent risk should be treated as negligible for NEOs that are tens to hundreds of meters in diameter. Read those two statements together. The first says the swarm probably exists. The second says nobody has proven it is safe to ignore. And the entire planetary defense framework is built on the implicit assumption that coherent risk can be ignored, because the framework was not designed with coherent risk in mind. The surveys are optimized for random threats. The deflection timelines assume years of warning. enough time to launch a kinetic impactor or gravity tractor mission. The risk models assume stochastic distributions that spread probability evenly across time. And there is a subtler problem that I think is worth naming. The surveys are optimized to find objects on well-determined orbits, objects that have been observed multiple times over multiple nights, with enough data points to compute a reliable trajectory. That works for isolated asteroids on stable orbits. It works less well for a swarm of objects that are faint, dark, potentially numerous, and observable only during narrow encounter windows. A 20-meter cometary fragment at 3% albedo, approaching from the Taurid corridor during a 3-week window, might appear in only a handful of survey frames before it either passes by or enters the atmosphere. The standard pipeline might flag it as a tracklet, a short arc of detections insufficient to compute a reliable orbit, and park it in a to-be-confirmed queue rather than generating an immediate alert. The system is designed for a different cadence of threat than what the swarm hypothesis describes. I do not want to overstate this. Boslow is not saying the system is broken. He is saying the system has not been tested against a specific class of threat that has observational support. And the gap between has not been tested and has been tested and found adequate is exactly the gap this investigation is sitting inside. Part 9, what the paper actually says. I want to spend time on the Boslow paper because it has been widely covered and, in my assessment, frequently reduced to a headline that loses what makes it genuinely important. The paper was published in Acta Astronautica, volume 238, page 710, as part of the proceedings of the 9th International Academy of Astronautics Planetary Defense Conference, held in May 2025 in Stellenbosch, near Cape Town, South Africa. The PDC is not a general astronomy conference. It is the premier international forum specifically dedicated to the threat of near-Earth object impacts, a gathering of the people whose professional responsibility is to protect the planet from cosmic debris. Attendees include NASA's Planetary Defense Coordination Office, the European Space Agency's Space Safety Program, national space agencies from around the world, university researchers, military planners, and civil defense specialists. Papers presented at PDC undergo peer review by people who evaluate impact risk for a living. A paper accepted into PDC proceedings carries a level of institutional seriousness that is distinct from a paper published in a general astronomy journal. The authors are Mark Boslow, Peter Brown, David Clark, Paul Wiegert, and Quanji Ye. Brown, Clark, and Wiegert are at Western University in Ontario, Canada, home to one of the world's leading meteor physics research groups, with decades of published work on bolide dynamics, fireball networks, and meteoroid stream characterization. Brown, in particular, is one of the most cited meteor scientists in the world, and his research on the Chelyabinsk airburst helped establish the energy and trajectory parameters that all subsequent analyses have built on. This is not a fringe paper published in an obscure venue by outsiders to the field. It is a mainstream planetary defense assessment authored by researchers at the center of the discipline. So what does the paper actually argue? Let me walk through the 3 core claims, and then I want to address a 4th element that most summaries omit entirely. First, the paper establishes that the Taurid Resonant Swarm has observational support from multiple independent lines of evidence. The 2015 European Fireball Network campaign confirmed the 7:2 resonance at the meteoroid scale with unprecedented precision. The 1975 Apollo seismometer data showed a 10-fold increase in lunar impacts during a predicted swarm encounter, a line of evidence that is entirely independent of optical meteor observations. Enhanced fireball activity has been observed in every swarm predicted year, going back to 1995, a streak of correct predictions that spans 3 decades, and the 2015 discovery of near-Earth asteroids. 2015 TX24 and 2005 UR, inside the resonant branch, extends the size range of confirmed swarm-associated objects from sub-meter meteoroids to 100-meter class asteroids. The evidence is not a single thread. It is a cable of multiple fibers, each from a different measurement technique, all pointing in the same direction. Second, The paper calculates the timing and geometry of the next close approaches with enough precision to plan observation campaigns. November 2032 on the night side. Observable, testable, the cleanest window we will get for decades. June 2036 on the day side. Harder to observe, and if a large object approaches from the sun's direction, detection will be late or impossible using current ground-based assets. The paper also identifies intermediate approached windows in June 2026, right now, and 2029, which offer opportunities for preliminary observations that could sharpen the constraints before the critical 2032 encounter. Third, and this is the element that gets systematically lost in headlines. The paper does not claim that a Tunguska class or Chelyabinsk class impact is likely in 2032 or 2036. It does not even claim that the swarm definitely contains dangerous objects at high density. What it says, and the precision of this language matters, is that the risk from airburst-sized near-Earth objects might be larger than currently estimated, and that the technology to test whether the swarm contains those objects exists right now. The paper frames the question as testable, the test as affordable, and the consequence of not testing as an unquantified risk that the planetary defense community is implicitly accepting without having examined it. Fourth, and this is the part I think most coverage misses entirely, the paper addresses the nature of risk itself. Standard planetary defense risk models treat impact probability as stochastic, randomly distributed in time, uncorrelated from year to year. But Boslow and his co-authors argue that the Taurid swarm provides an existence proof that risk can be coherent, concentrated in specific time windows by a known physical mechanism, and they note that there is no theoretical or observational evidence establishing that this coherent risk is negligible at the sizes that matter. The absence of evidence is not evidence of absence. Nobody has looked hard enough at the right time with the right instruments to rule out a significant population of dangerous objects inside the resonant swarm. And until someone does, the risk remains unquantified, which is a fundamentally different status than low. Boslow frames this with a clarity that I think the media coverage has not adequately conveyed. The swarm will make close approaches. Telescopes can observe. If dangerous objects are there, we should be able to detect them, especially in 2032, when the geometry puts the swarm on the night side. If the observations come back clean, the hypothesis is weakened and the risk framework stands as is. If the observations reveal previously unknown objects inside the resonant corridor, the framework needs revision. That is a clean, honest, testable scientific argument. And it is exactly the kind of argument that tends to get flattened into either we are all going to die or nothing to worry about. Both of those readings are wrong. The correct read is we have a hypothesis with substantial supporting evidence, a prediction with specific dates and geometries, and the instrumentation to test it decisively. The question is whether we will. And there is a new variable in this equation that did not exist when Boslow began this line of research. A telescope in the mountains of Chile that is already rewriting what we thought we knew about the small body population of the solar system. It changes the calculus of this entire investigation. Part 10, what 2032 looks like. So let me walk you through what happens in November. 2032, because the geometry of this encounter is something I have spent more time with than almost any other element of this investigation. And the geometry is why Boslow calls it the critical observation window. Earth's orbit will carry it near the densest predicted region of the Taurid Resonant Swarm during the first 3 weeks of November 2032. And because November is the nighttime Taurid season, the debris approaches Earth from the anti-sunward side. The approach geometry puts the swarm on the night side of the planet. Objects in the swarm, if they exist at dangerous sizes, would be receding from us, moving away from Earth into the dark sky after their closest approach, which means telescopes on the ground can see them, track them, measure their brightness, compute their orbits, estimate their sizes, and determine whether any are on trajectories that bring them dangerously close to Earth in that encounter or in future ones. This is the test, the clean test, the one Boslow has been building toward for the better part of a decade, but the test only works if the right instruments are pointed at the right part of the sky during the right weeks. And that requires planning, funding, and institutional commitment, none of which materialize automatically. 6 years sounds like a generous lead time. In the world of telescope scheduling and survey planning, it is not. Major observational campaigns take years to design, fund, and coordinate. The survey strategy has to be calibrated for the expected brightness and motion rates of Taurid swarm objects. The data pipeline has to be able to handle the volume of detections. And competing priorities, there are always competing priorities in astronomy, have to be managed. And here is a detail that makes the 2032 window even more significant than the orbital geometry alone would suggest. The moon will be new during the peak Taurid activity period that month. New moon on November 9th, 2032. No moonlight interference. Dark skies at exactly the right time. This is not something anyone planned. It is orbital mechanics doing us a favor. The lunar cycle is 29.5 days, and the Taurid peak shifts slightly from year to year, and in 2032, the two cycles happen to align in the most favorable way possible for ground-based observation. To appreciate why this matters, consider what observing faint near-Earth objects actually requires. These are not bright stars or obvious planets. A 20-meter cometary fragment at a typical Taurid swarm distance, say a few million kilometers, would appear as a faint point of light, moving slowly against the background stars, with an apparent brightness well below naked eye visibility. Detecting it requires a sensitive telescope, dark sky, and multiple exposures over a period of hours. Moonlight raises the sky background, the diffuse glow that competes with faint objects, and can render marginal detections impossible. A new moon during the peak observation window means the darkest possible sky during exactly the nights when the most sensitive measurements need to be made. It means 2032 is not merely a good observation window. It may be the best window we will get in our lifetimes. The alignment of swarm proximity, night-side geometry, and new moon lunar phase creates a combination that does not repeat on any schedule a human career can wait for. If the planetary defense community does not take full advantage of the 2032 window, the next comparably favorable opportunity may not arrive for decades, by which point the question of what is in the swarm will still be unanswered, and the 2036 encounter will have come and gone without the information we needed to assess it properly. If the observations in 2032 come back clean, if wide-field surveys and targeted campaigns search the resonant corridor and find nothing larger than the meteoroids we already know about, the swarm hypothesis is substantially weakened at the sizes that matter for planetary defense. We breathe easier. The existing risk models stand. The probability calculations remain valid. And the planetary defense community can turn its full attention back to the random threat model with justified confidence. If the observations reveal previously unknown objects in the 10-meter plus range, clustered inside the 7-2 resonance, the conversation changes overnight. And I want to be specific about what changes means operationally, because abstract statements about changing conversations do not convey the real-world implications. If the 2032 observations find, say, a dozen previously unknown objects in the 20 to 50 meter range with orbits consistent with the resonant swarm, the immediate consequence is a cascade of follow-up observations. Every major telescope with time available gets pointed at those objects. Orbits are refined from weeks of data to months of data. Future close approaches to Earth are computed not just in 2036, but for the next century. And for the first time, we would have an empirical measure of the swarm's dangerous object density, not an estimate based on extrapolation from fireball data. An actual count. That count would then be used to recalculate the risk for the June 2036 encounter. The dayside approach, the beta Taurid geometry, the one where the objects come from the direction of the sun. And depending on what that recalculation shows, the response could range from continued monitoring to active preparation of civil defense measures for regions under the predicted ground track. I want to be measured about this. The most likely outcome of the 2032 observations is that we find very little. The swarm is probably sparse at dangerous sizes. But probably sparse is not confirmed sparse, And the purpose of the 2032 window is precisely to convert probability into measurement. That is what science does. That is what planetary defense requires. The strategic logic is stark. 2032 is the observation window. 2036 is the consequence window. What we learn in the first determines how seriously we need to prepare for the second. Part 11. What 2036 looks like. June 2036. The beta Taurid geometry. The same approach direction as the Tunguska event of 1908. I need you to visualize this clearly because the operational difference between 2032 and 2036 is not subtle. It is structural. It changes what is possible. In November 2032, objects in the swarm are visible against dark sky. Telescopes can find them, track them, compute orbits, and determine whether any are on a collision course with Earth. We would have days to weeks of advanced knowledge, potentially enough time for evacuation planning if something were headed for a populated area. Not deflection. The timelines for deflection require years, not weeks. But awareness, knowledge, the chance to move people out of the way and position emergency response before the event. In June 2036, the swarm approaches from the direction of the sun. Ground-based optical telescopes cannot see objects that are closer to us than the sun and lit from behind. The objects would be invisible until they passed Earth and receded into the night sky, or until one of them entered the atmosphere. And if an object enters the atmosphere from the sunward side, traveling at the velocities typical of Taurid meteoroids, roughly 30 kilometers per second, 67,000 miles per hour, the time between any conceivable detection and impact is measured in seconds. Not minutes, not hours, seconds. There is no evacuation in seconds. There is no warning in seconds. There is only the flash and then the shockwave. This is not a theoretical concern. It is an operational reality that the planetary defense community has grappled with for years. The Chelyabinsk object in 2013 arrived from the sunward direction. Nobody saw it coming, and that was a 20-meter object, too small and too close to the sun's glare for any existing telescope to have detected. If a 40 or 50-meter object approaches from the same geometry, the detection problem is identical. The object is larger, but it is still dark, still fast, still coming from the worst possible direction for ground-based observation. And the beta Taurid window, late June into mid-July, is exactly that geometry. Every year. The only thing that changes is whether the resonant swarm is nearby, concentrating more objects into the corridor Earth is crossing. Boslow does not mince words. The swarm will come from the direction of the sun in 2036, he says, so fireballs will not be seen in our blue skies unless they are extremely bright. That means a Chelyabinsk-class object, 20 meters, 500 kilotons, could arrive with zero warning, and a Tunguska-class object, 40 to 50 meters, 5 to 15 megatons, would be even harder to detect optically, because cometary fragments tend to be among the darkest objects in the solar system. Low albedo, poor reflectors. They absorb sunlight rather than bouncing it back toward telescopes. They are, in the most literal sense, nearly invisible. There is a potential mitigation. NASA's Near-Earth Object Surveyor, NEO Surveyor, is a space-based infrared telescope designed specifically to find objects that reflect little visible light. It detects heat, not reflected sunlight, which makes it effective against exactly the class of dark, low albedo objects that ground-based surveys struggle with. Even a cold, dark cometary fragment radiates infrared energy, thermal emission from solar heating of its surface, and an infrared telescope in deep space can detect that emission regardless of the object's visible reflectivity. NEO Surveyor would orbit at the Sun-Earth L1 Lagrange point, roughly 1.5 million kilometers sunward of Earth, giving it a vantage point from which objects approaching from the sunward direction would be detectable against the cold background of deep space. NEO Surveyor is currently targeting launch in late 2027. If it is operational by 2036, if commissioning and calibration proceed smoothly, which typically requires 6 to 12 months after launch. And if its survey cadence includes coverage of the Taurid corridor during the June beta Taurid window, it could potentially detect incoming objects that no ground-based system would see. But that is a chain of conditional statements. If it launches on time, if commissioning proceeds on schedule, if its survey strategy is configured to prioritize the relevant part of the ecliptic during the relevant weeks. Each link in the chain is reasonable. None is guaranteed. Space missions have historically experienced substantial delays. James Webb. Space Telescope was originally planned for launch in 2011 and did not fly until 2021. NEO Surveyor has navigated its own budget and schedule challenges, and the gap between reasonable expectation and operational reality is where planetary defense planners lose sleep. Scientific American, in its coverage of the Boslow paper, noted that Boslow specifically called for observations during the intermediate approach windows, June 2026 and 2029, as well as the major encounters in 32 and 36. By then, scientists may have a shiny new tool to investigate the swarm, the article noted, referring to NEO Surveyor. But the word may is doing load-bearing work in that sentence, and the question of whether may converts to will is not a scientific question. It is a budget question, an institutional question, and a political question. Those questions get answered on different timescales than orbital mechanics. Jupiter does not care about continuing resolutions. I do not think the planetary defense community will miss the critical windows entirely. The awareness is there. The paper has been presented at the highest profile planetary defense venue on the planet. The case has been made. But I have seen enough institutional processes in my years covering these topics to know that awareness and funded action can remain separated by committee deliberations, competing priorities, and budget constraints longer than anyone expects. And the Taurid swarm operates on its own schedule. It orbits. It arrives. And if the instruments are not watching when it passes, we learn nothing and carry the same unquantified risk forward into the next encounter and the one after that. Part 12, The Conspiracy and the Physics. I want to address something directly, because this topic attracts claims that range from legitimate scientific debate to outright fabrication, and the people asking those questions deserve actual answers. Not dismissal, not condescension, and not fear-mongering. So I'm going to take each major claim in turn and give it the response it deserves. The first claim is the Younger Dryas impact hypothesis, the idea that a fragment of the Taurid complex struck Earth roughly 12,900 years ago, caused widespread fires across North America, triggered the extinction of Ice Age megafauna including mammoths and saber-toothed cats, and pushed the global climate back into near-glacial conditions for 1,300 years. This is a serious claim, advanced by serious researchers, published in peer-reviewed journals, and it is contested. Fiercely. I'm going to walk through this carefully because it is the honest Steelman, the one alternative framing that has genuine peer-reviewed scientific substance and that structurally connects to the Taurid swarm investigation in a way that cannot be dismissed with a wave of the hand. The hypothesis was first proposed in 2007 by Richard Firestone and a team of collaborators. They pointed to a thin geological layer at multiple sites across North America and parts of Europe, the Younger Dryas boundary layer, that contained what they argued were impact markers, nanodiamonds, magnetic microspherules, and elevated concentrations of platinum group elements, including iridium. These are the kinds of signatures associated with cosmic impacts. The Cretaceous Paleogene boundary, the layer that marks the asteroid impact that killed the non-avian dinosaurs, Taurid, contains similar markers, though at vastly larger concentrations. Firestone's team argued that the Younger Dryas markers indicated a Tunguska scale or larger airburst from a Taurid complex fragment, large enough to ignite continent-scale wildfires and inject enough material into the atmosphere to trigger abrupt cooling. The debate that followed has been one of the most contentious in modern Earth science. I am going to present both sides with the specificity they deserve. Against the hypothesis, multiple teams have failed to replicate some of the original findings. The nanodiamonds, in particular, have been questioned. Some analyses have suggested they may be Lonsdaleite, a hexagonal form of carbon that can be produced by non-impact processes. Boslow himself has been one of the most rigorous critics. He co-authored a detailed rebuttal of the hypothesis. He helped prompt a journal to retract a paper that claimed the ancient city of Tal el Hammam in Jordan was destroyed by a Tunguska-scale airburst. Boslow demonstrated that the paper fundamentally misunderstood the physics of how airbursts work, miscalculating the pressure and thermal effects at the surface. His published research has consistently argued that the Younger Dryas impact proponents have overstated the evidence and misapplied airburst models. For the hypothesis, proponents have continued to publish. They have reported additional impact markers at new sites around the world, in Syria, South Africa, Chile, and across Europe. The platinum anomaly at the Younger Dryas boundary has been replicated independently by multiple groups, and more recent work has focused on high-temperature impact spherules, tiny glassy beads formed when material melts and resolidifies at temperatures far above what wildfires can produce. Some of this work has survived peer review in high-impact journals. Here is how I hold this. The Younger Dryas impact hypothesis is not proven. The evidence is actively contested, key findings have not replicated cleanly, and the physical mechanisms proposed by proponents have been challenged on energy budget grounds by scientists, including Boslow, who understand airburst physics at a level of detail that most proponents do not. But it is also not conclusively falsified. The debate is live, and the fact that the Taurid complex demonstrably contains near-Earth asteroids hundreds of meters across, objects capable of producing airbursts far larger than Tunguska, means the physical possibility of a Taurid-linked impact of that scale is not zero. It is just not established. What I will not do is treat the Younger Dryas hypothesis as established fact and use it to inflate the threat from the current Taurid swarm. That would be dishonest. The evidence for the swarm's composition and risk stands on its own, and it is strong enough to demand investigation without borrowing authority from an unresolved debate. The second claim I want to address is more straightforward. You will find, across social media and some YouTube channels, posts claiming that the Taurid swarm represents an imminent extinction-level threat, that governments are suppressing information about incoming impacts, and that 2032 will be a catastrophe. This is wrong. It is wrong in a specific, quantifiable way that I can demonstrate. The largest objects confirmed inside the Taurid resonant branch are several hundred meters across. An object of that size impacting Earth would be regionally catastrophic. It could produce a devastating tsunami if it hit ocean, or flatten a major metropolitan area if it hit land. The casualties could be in the hundreds of thousands. That is a nightmare scenario, but it is not an extinction event. Extinction-level impacts require objects roughly 10 kilometers in diameter, or larger, the scale of the Chicxulub impactor that ended the Cretaceous. The Taurid progenitor Comet may have been that size when it was intact, but it is gone. It broke apart tens of thousands of years ago. What remains are the fragments, and the fragments, even the largest known ones, are 3 to 4 orders of magnitude below the extinction threshold in terms of impact energy. The third claim I want to dispatch quickly: HARP, directed energy weapons, weather modification, and the assertion that human technology can steer or trigger cometary impacts. The physics here is unambiguous. The energy budget of a Chelyabinsk-class airburst is 500 kilotons of TNT, roughly 2 times 10 to the 15th joules. HARP's maximum effective radiated power is 3.6 megawatts. That is 3.6 times 10 to the 6th watts. The mismatch is not a matter of degree, it is 12 orders of magnitude. The difference between HARP's output and a Chelyabinsk airburst is the difference between a flashlight and the sun. You cannot steer a comet fragment with a radio antenna. The energy is not there. It is not even in the same conversation. The real concern, the one the evidence supports, is not that someone is causing impacts. It is that natural impacts may be concentrated in time and approach direction in ways that our detection architecture was not built to handle. And that concern is alarming enough on its own merits without any embellishment. Part 13, the telescope that changes everything. In April 2026, 2 months ago, the Vera C. Rubin Observatory in Chile reported something that, in my assessment, represents one of the most significant developments in planetary science this decade. Its early survey data, collected during optimization runs in the summer of 2025, before the main 10-year legacy survey of space and time had even officially started, had already identified more than 11,000 new asteroids. I want to put that number in context. The Minor Planet Center, the international clearinghouse that maintains the official catalog of all known asteroids, receives discovery submissions from dozens of surveys worldwide. 11,000 new asteroids in a single data submission is the largest single batch submitted in the past year, and this came from a telescope that was still being calibrated, still running preliminary software, still working through the early optimization phase of a survey that is designed to run for a decade. The discoveries were confirmed by the International Astronomical Union's Minor Planet Center. Among them were roughly 380 trans-Neptunian objects, icy bodies orbiting beyond Neptune, some on extremely large and elongated orbits that hint at the gravitational architecture of the outer solar system, and 33 previously unknown near-Earth asteroids. The data was collected over a period of about a month and a half during the summer of 2025, and the discoveries came in 3 bursts: 73 during the first test observations with Rubin's commissioning camera in late 2024, 1,514 during the first look observations in April and May 2025, and the most recent 11,000 from the early optimization surveys. The scale of this ramp-up is staggering, and it has not peaked, not even close. One of those near-Earth discoveries, detailed in a peer-reviewed paper led by Sarah Greenstreet at NSF NOIRLab, the lead of Rubin Observatory's Near-Earth Objects and Interstellar Objects Working Group, turned out to be the fastest spinning asteroid larger than 500 meters ever found. An object designated 2025 MN45, roughly 700 meters in mean diameter, rotating every 1.88 minutes. For an object that size to hold together at that spin rate, it needs internal cohesion far beyond what a loose rubble pile could provide. It suggests a monolithic or heavily cemented interior, a finding that challenges conventional assumptions about asteroid structure and has implications for deflection strategies. But what matters for this investigation is not the spin rate, it is the detection sensitivity. And the numbers that Rubin's team has projected for the full LSST survey connect directly to the Taurid Swarm question. Once operating in full survey mode, CIUS, expected to begin later this year, Rubin is projected to detect an additional roughly 90,000 new near-Earth objects. The observatory projects that it will nearly double the number of known near-Earth objects larger than 140 meters, bringing detection completeness from roughly 50% to around 70% at that size threshold. Dmitry Vavilov at the University of Washington, who presented Rubin's asteroid discoveries at the 57th Lunar and Planetary Science Conference in March 2026, described the current discoveries as just a tiny taste of the eventual asteroid smorgasbord, anticipated from the full 10-year survey, and a clue to the existence of whole undiscovered populations. 70% completeness, which means 30% of the objects large enough to devastate a city remain undiscovered as of right now. 30% of a population that numbers in the tens of thousands. That is thousands of objects somewhere out there, orbiting the sun, occasionally crossing Earth's path, that we have not found yet. And the question this entire investigation has been building toward is whether any of that 30% is hiding inside the Taurid Resonant Swarm, whether the specific orbital corridor where Jupiter's gravity concentrates debris contains objects that existing surveys have missed, not because the surveys are inadequate for their design purpose, but because their design purpose did not include searching for dark, clustered cometary fragments in a specific part of the sky during specific weeks. Rubin can look. Its 8.4-meter primary mirror collects light across an enormous field of view, 9.6 square degrees in a single exposure, roughly 40 times the apparent area of the full moon. Its 3.2 gigapixel camera, the most powerful astronomical digital camera ever built, developed at SLAC National Accelerator Laboratory, can image these vast sky patches with sensitivity sufficient to detect objects that are several magnitudes fainter than what current surveys can reach. And its rapid cadence, returning to the same patches of sky repeatedly over days, weeks, and months, is specifically designed to detect objects that move against the background stars. Faint, fast, small, exactly the profile of a dark cometary fragment drifting through the inner solar system at 20 or 30 kilometers per second. The Arcs of Paper by Quanji Ye, presented at the 2025 Planetary Defense Conference, names Rubin explicitly. Future wide-field facilities, such as the Vera-C-Rubin Observatory, the paper states, could take advantage of the Taurid Resonant Swarm's close approaches in the 2020s and 30s and validate the constraints on the asteroid-sized objects in the swarm. And Boslow, in his Scientific American interview, was more pointed. He called for observations specifically during the June 2026 and 2029 intermediate approach windows, suggesting that if Rubin's survey strategy covers the relevant part of the sky during those windows, the telescope has the sensitivity to detect objects that no previous instrument could have found. The timing is almost unreasonably good. The most capable wide-field survey telescope in history arrives just as the question becomes testable. The Taurid Resonant Swarm has been debated for more than 30 years. The observational tools to resolve the debate are now coming online. And the encounter calendar, 2026, 2029, 2032, 2036, provides a sequence of escalating tests, each one narrowing the uncertainty. I have said throughout this investigation that I will not overstate the evidence, so I will not. What I will say is this: if the swarm contains dangerous objects, we are closer to knowing than we have ever been. And if it does not, if Rubin and NEO-Surveyor and the ground-based campaigns search the resonant corridor and find nothing but dust and fireballs, that is a finding too. A finding that the current planetary defense framework is correct, that impact risk really is random, that the models were right all along. Both outcomes matter. Only one of them lets us relax. Part 14. Interpretation 1. The swarm is sparse and the risk is background. I am going to present 3 ways to read the evidence we have assembled in this investigation. Each one is grounded in published science. Each one has named researchers behind it, and I am going to give each one genuine weight, including the most reassuring one, because the data does not tell us which interpretation is correct. What it tells us is what each one costs if it turns out to be wrong. The first interpretation is the most reassuring, and it deserves to be presented fairly and completely because it is not wrong. It is reasonable. It accounts for the data. And I want to be clear about that because I've seen too many investigations, including ones I respect, present the benign interpretation as a straw man to be knocked down on the way to the scary conclusion. That is not what is happening here. Under this interpretation, the 7-2 resonance with Jupiter is real and confirmed. It concentrates meteoroids, objects from dust size to a few meters across, into a coherent swarm. The 2015 European Fireball Network campaign proved this at the meteoroid scale with a precision that is not seriously disputed. But the jump from meteoroids to asteroids, from fireballs to Tunguska-class objects, is exactly that: a jump, an extrapolation, and there is no direct observational evidence that the resonance concentrates large objects at densities significantly above the background near-Earth population. The 2 asteroids found inside the resonant branch, 2015 TX-24 and 2005 UR-ISU, could be coincidental occupants of that orbital space. The 7-2 resonance is a real dynamical feature, but it is not an exclusive address. Other near-Earth objects pass through it or occupy it temporarily without being genetically related to the Taurid complex. The spectral data from Popescu and colleagues in 2014 showing that 5 out of 6 large asteroids proposed as Taurid members had compositions inconsistent with cometary origin, supports the view that the large body population in that orbital regime may be dominated by ordinary main belt escapees rather than fragments of the progenitor comet. And there is a more recent study that strengthens this interpretation. A 2025 paper in the Planetary Science Journal attempted to place a direct observational limit on the mass of the Taurid Resonant Swarm at sub-100 meter sizes. The constraints were not tight. The data allowed for a wide range of possible populations, but the upper limits were consistent with a swarm that is sparse enough at dangerous sizes to pose no meaningful elevation of risk above the random background. If this constraint holds, the swarm is real at the fireball level, but essentially empty at the sizes that matter for civil defense. There is also a direct observational test that came back negative. In 2019, Canadian astronomers at Western University conducted a targeted search for hypothesized asteroids roughly 100 meters in diameter from the Taurid swarm. They searched between July 5th and 11th, and again from July 21st through August 10th. No new objects were reported. That is not a definitive null result. The search covered limited sky area during limited windows, and the objects in question might be dark enough to evade the telescopes used. But it is consistent with interpretation 1. If the swarm were densely populated with 100-meter objects, some should have been found. None were. Under this interpretation, the enhanced fireball activity in swarm years reflects the concentration of small meteoroids, objects that produce impressive light shows, but pose zero threat to anyone on the ground. The Apollo seismometer data from 1975 reflects an increase in small impactors hitting the moon, consistent with the swarm hypothesis, but not diagnostic of larger objects hiding in the stream, and the risk calculations remain fundamentally sound. Impacts from dangerous-sized objects are random. The resonance adds a small, manageable, and possibly negligible perturbation to the background rate. I want to be explicit. This interpretation has support. It is not a straw man. If someone pressed me, and I will come back to what I actually think, this is probably the most likely reading of the current evidence. The swarm exists at the meteoroid scale. At the asteroid scale, the evidence is suggestive but not conclusive, and the base rate argument, or that the near-Earth object population is well studied at larger sizes and no anomalous clustering has been observed in the decades of systematic surveys, is a genuine piece of evidence. The Catalina Sky Survey, Pan-STARRS, Atlas, and their predecessors have collectively observed tens of thousands of near-Earth objects. If the Taurid Resonant Swarm contained hundreds or thousands of objects in the 10 to 100 meter range, it is reasonable to ask, why hasn't a systematic survey stumbled across them? The answer might be that the objects are too dark and too small for current surveys. Or the answer might be that the objects are not there. The precautionary instinct, what if the worst case is true, is valuable, but it has to be balanced against the base rate evidence. The planetary defense community has been watching the sky for decades. The fact that no swarm-associated dangerous objects have been identified, while not conclusive, is more consistent with a sparse swarm than a dense one. But probably the most likely is not certainly correct. And in planetary defense, a field where the consequences of being wrong range from a shattered ice rink in Chelyabinsk to a flattened city, the distinction matters enormously. The precautionary instinct says, if there is even a small chance the swarm contains dangerous objects, we should look. The cost of looking is measured in telescope time and grant funding, millions of dollars. The cost of not looking, if interpretation 1 is wrong, is measured in a currency nobody wants to spend. And the asymmetry between those two costs is the entire justification for Boslow's paper. Part 15, Interpretation 2, Enhanced but Bounded Regional Risk. The second interpretation takes the same evidence and follows it without adding assumptions. No extrapolation into worst-case territory. No cherry-picking the most alarming data points. Just following the physical logic of the resonance mechanism and the population estimates to their natural conclusion. Under this interpretation, the 7:2 resonance concentrates objects across a range of sizes, not just at the meteoroid scale. The physical mechanism, Jupiter's gravitational shepherding, has no known size cutoff. There's no principle of orbital mechanics that says the resonance concentrates 20 centimeter meteoroids but ignores 20-meter asteroids. The gravitational perturbation acts on everything in the stream. Larger objects have more inertia, so they respond more slowly, but over thousands of years and millions of orbital periods, the effect accumulates. If dust is concentrated, rocks should be too. The question is not whether the mechanism works at larger sizes. The question is how many large objects are there to be concentrated. Quanji Ye's estimate provides one answer: roughly 1,000 Chelyabinsk-class objects inside the resonant swarm. That estimate, even with its caveats, translates to a meaningful statement about risk. Not a statement that anyone should panic about, but a statement that is distinct from the background. To make this concrete, the estimated rate of Chelyabinsk-class events from the entire near-Earth population, random, unpredictable, from any direction, is roughly once every 50 to 100 years. That is the stochastic background. Under Interpretation 2, the swarm adds a periodic enhancement on top of that background. Even a modest enhancement, say a factor of 3 during swarm encounter windows, would mean that a given 3-week period in November of a swarm year carries roughly the same probability of a Chelyabinsk-class event as an entire decade of random background risk. That is not a high probability in absolute terms, but it is concentrated, it is predictable, and it is, in principle, something the system could prepare for. 1,000 20-meter objects concentrated into a specific orbital corridor that Earth crosses during predictable windows would mean that during swarm encounter years, and only during those years, the probability of a regional airburst is elevated, not dramatically, not to the point where an impact becomes likely in any single year, but elevated above the random background by a factor that, depending on the actual population density, could range from negligible to significant, and the implications scale with object size. If the population includes not just 20-meter objects, but also 40-meter objects, Tunguska class, the energy per event increases by roughly an order of magnitude. A single 40-meter airburst over a populated area during a swarm encounter window would be the most destructive natural event in modern history. It would not end civilization, but it would reshape the planetary defense conversation permanently. 1,000 20-meter objects concentrated into a specific orbital corridor that Earth crosses during predictable windows would mean that during swarm encounter years, and only during those years, the probability of a regional airburst is elevated. Not dramatically, not to the point where an impact becomes likely in any single year, but elevated above the random background by a factor that might be 2 or 5 or 10. The data does not constrain it precisely, but even a factor of 3 or 4 applied to the 3-week November 2032 encounter window would mean that the probability of a Chelyabinsk-class event during those 3 weeks is higher than during any comparable 3 weeks in a non-swarm year. This is the meteorological analogy I keep returning to, and I think it captures the right way to hold this. We do not treat tornado risk as uniform across the calendar. We know that March through June in the central United States is tornado season. We do not panic about it. We do not evacuate the Great Plains every spring. But we do allocate resources differently during those months. We staff weather offices at full capacity. We issue watches and warnings with lower thresholds. We pre-position emergency supplies. We run severe weather awareness weeks. The National Weather Service's Storm Prediction Center in Norman, Oklahoma, shifts its forecasting posture during those months, issuing outlooks that explicitly quantify the probability of severe weather in specific geographic areas days in advance. The infrastructure responds to the reality that risk is temporally concentrated, and crucially, we reach that operational posture not through theoretical modeling alone, but through decades of observation. The tornado climatology of the United States was built on data, thousands of events, carefully cataloged, geographically mapped, temporally organized. The forecasting framework that saves lives every year rests on an empirical foundation. Theory alone would not have been sufficient. Somebody had to count the tornadoes. If the Taurid swarm concentrates impact risk into periodic windows, a few weeks every 7 to 10 years, the same logic applies. The question is not whether we can eliminate the risk. We cannot. The question is whether we are treating the high-risk windows differently from the background periods, whether our planetary defense posture shifts during swarm encounter years, whether the telescopes are pointed, whether the data pipelines are ready, whether the civil defense community even knows the windows exist. What would a risk-aware posture look like? It would not require much. A modest reallocation of telescope time during swarm encounter years, directing existing assets toward the Taurid corridor during the predicted peak weeks, alerting the Planetary Defense Coordination Office that a coherent risk window is active, ensuring that the Atlas and Catalina surveys are configured to detect objects moving at Taurid consistent velocities from Taurid consistent directions. None of this requires new infrastructure. None of it requires new telescopes. It requires only acknowledging that risk may not be uniform and adjusting existing operations accordingly. Right now, the answer to all of those operational questions is mostly no. The planetary defense system treats every week of every year the same way because the underlying risk model says they are the same. And the institutional reason is that interpretation 1 knows the assumption that the swarm is probably sparse and the risk negligible has been the default operational posture, not because it has been confirmed by measurement, but because it has not been disconfirmed. The absence of evidence has been treated as evidence of absence, and Boslow's paper exists at its core to argue that we should replace assumption with measurement before we bet the safety of populated areas on it. Part 16, Interpretation 3I, a loaded corridor. The third interpretation is the most concerning, and I am going to present it with precision because precision is what separates a legitimate concern from irresponsible alarm. And the distance between those two things matters in every sentence. Under this interpretation, the Taurid complex, the debris of a comet that may have been 100 kilometers across when it entered the inner solar system, a comet that broke apart over the course of 10 to 30,000 years, contains a significant population of objects in the 10 to 300 meter range. These objects are dark, cometary fragments with surfaces that have been baked, desiccated, and blackened by millennia of solar processing. They are inactive, no longer outgassing, no longer producing the tails or comas that make comets visible to surveys designed to find them. They are effectively stealth asteroids. Dark rocks on dark orbits, drifting through a stream that Earth intersects twice a year. The 7-2 resonance concentrates a subset of these objects into a denser corridor, the resonant swarm. And when Earth passes near the center of that corridor, the probability of encountering one of these objects is elevated for a period of days to weeks, not elevated to the point where an impact becomes probable in any single encounter, but elevated in a way that compounds across encounters, across decades, across centuries. Under this interpretation, the Tunguska event of 1908 was not a random impact from a random direction. It was a Taurid swarm encounter. The timing, June 30th, the peak of the beta Taurid shower. The trajectory, from the same radiant as the beta Taurid stream, arriving from the sunward side exactly as the geometry of the June encounter predicts. The likely composition, consistent with a low-density cometary fragment rather than a rocky asteroid. And Boslow's own computational modeling. His team ran three-dimensional hydrocode simulations of an airburst with entry parameters, azimuth, entry angle, velocity, consistent with the date, time of day, and location for a beta Taurid object associated with Comet Encke. And the shape and orientation of the resulting blast wave footprint was a good match to the published maps of tree fall in the Tunguska region. If that match is meaningful, and it is circumstantial, not definitive, and I need to say that clearly, and I am saying it, then the Tunguska object was not a random visitor. It came from a known debris stream, a stream we pass through every June, a stream whose densest region approaches Earth at predictable intervals. And the next close approach at that same beta Taurid geometry is 2036. The most concerning element of this interpretation is not the probability of a single large event. It is the detection gap. And I want to walk through this gap with specificity because it is the operational core of why interpretation 3, even at low probability, demands a response. A 50-meter object, roughly 3 times the diameter of Chelyabinsk, delivering an explosive yield of 5 to 15 megatons, 30 to 100 times the energy of the Chelyabinsk airburst, approaching from the direction of the sun during the beta Taurid window, would be invisible to every ground-based optical survey currently operating. Ground-based telescopes see objects by the sunlight they reflect. An object between us and the sun reflects its light away from us. It is backlit, like trying to see a bird flying directly in front of a floodlight. The object is there. It is real. It has mass and velocity and kinetic energy, but it is optically invisible from the surface of the Earth. The first indication of its arrival would be the flash. At a velocity of 30 kilometers per second, typical for a Taurid meteoroid, a 50-meter object would cross the distance from the edge of detectability to atmospheric entry in a time frame, measured in hours to minutes, not days or weeks. And if its albedo is low, if it is a dark cometary fragment, with a surface reflectivity of 3 to 5%, which is typical for carbonaceous objects, it would be at the very edge of even space-based infrared detection capabilities. If such an object detonated at high altitude over open ocean, it would produce a seismic event registering on ocean bottom seismometers, a thermal signature detectable by military infrared satellites, an atmospheric pressure wave measurable on infrasound arrays, and a spectacular, if short-lived, atmospheric disturbance. Fishermen and sailors in the vicinity would experience a terrifying event, but likely survive. If it detonated over a coastal city at lower altitude, if the entry angle and material strength conspired to push the burst point down to 5 or 10 kilometers above the surface, the shock wave could produce casualties in the tens of thousands and property damage in the billions. The thermal pulse alone, the brief flash of intense heat radiating from the fireball, could ignite fires across an area of tens of square kilometers. And unlike an earthquake or hurricane, there would be no warning, no evacuation order, no shelter-in-place advisory, no 15-minute lead time from an early warning system. The event would begin and end in the time it takes to blink. The Tunguska event in 1908 gives us the closest real-world reference point. The blast flattened 800 square miles of forest. The shockwave was detected seismically across Europe. The atmospheric disturbance was visible for nights across the continent, and that happened over one of the most remote, sparsely populated regions on Earth. The nearest settlement was roughly 35 miles from ground zero. If the same event occurred today over even a moderately populated area, a city of 100,000, a suburban corridor, a coastal region, the consequences would be qualitatively different. Not just damaged windows, not just flying glass and car alarms, collapsed buildings, fires, infrastructure failure, and the cascading effects that follow any urban disaster, disrupted water systems, overwhelmed hospitals, displaced populations, and the economic shock that radiates outward for months. I am not saying this is likely. I want that to be unambiguous. The most probable reading of the current evidence is interpretation 1 or 2. The swarm is probably sparse at dangerous sizes. The risk is probably close to the background rate. The word probably is doing real work in those sentences, and I am choosing it deliberately. But the cost of interpretation 3 being correct, combined with the fact that the tools to test it exist and the observation windows are approaching, is the core tension of this entire investigation. Low probability, high consequence, available test. That calculus, that specific combination is the textbook definition of a situation where spending the resources to look is not discretionary. It is required. Part 17, what we know and what we do not. I want to separate the confirmed from the uncertain from the unknown with as much precision as this investigation allows, because I believe the clearest service I can offer is an honest inventory of what the evidence actually supports. Confirmed. The Taurid complex exists. It is a broad debris structure associated with Comet Encke and likely originating from a much larger progenitor body that broke apart tens of thousands of years ago, extending across a significant arc of the inner solar system. Earth passes through it twice a year. The nighttime Taurids in October and November, the daytime Beta Taurids in June and July. This is settled observational fact, documented across decades of meteor observation by networks on multiple continents. The Taurid complex is not a hypothesis. It is a mapped, measured, repeatedly observed feature of the inner solar system. Confirmed, the 7-2 resonance with Jupiter concentrates meteoroids within the Taurid stream into a coherent substructure, the resonant swarm. Pavel Spirny's 2015 European Fireball Network campaign documented this with 113 fireballs, sharing tightly clustered orbital elements within the predicted resonant corridor. The Desert Fireball Network in Australia independently observed the same enhancement during the same window. Asher and Klug predicted the years of enhanced activity beginning in 1993, and enhanced activity was observed in every predicted year from 1995 through 2022, a streak of correct predictions spanning 3 decades and 7 independent encounter windows. The resonance is real at the meteoroid scale. This is not seriously disputed by any active researcher in the field. Confirmed. At least 2 near-Earth asteroids, Kesku 2015, TX24, and 2005 URDs, have orbits consistent with the resonant branch. Their presence in that orbital space is established by celestial mechanics. Additionally, Farine and Orofino have identified 88 probable members of the broader Taurid complex, with 67% showing evidence of ongoing cometary activity, a finding that supports the giant comet breakup hypothesis and suggests the complex is younger and more active than previously assumed. What is not confirmed is whether the 100-meter class objects inside the resonance are genetically related to the Taurid progenitor or are coincidental occupants of similar orbital space. Confirmed, the Vera C. Rubin Observatory is operational and has already demonstrated the ability to discover near-Earth objects that existing surveys missed, including 33 new near-Earth asteroids in its preliminary data release. Confirmed, the Apollo seismometers recorded a 10-fold increase in lunar impacts during the 1975 daytime Taurid swarm encounter, a finding cited by Boslow as supporting evidence for the swarm hypothesis. Uncertain, the population of objects in the 10 to 100 meter range inside the resonant swarm. Yi's estimate of roughly 1,000 Chelyabinsk class objects is a scenario dependent on assumptions about orbital distributions that have not been validated at larger sizes. The actual number could be higher or lower by an order of magnitude, and the sensitivity of the risk calculation to this number is extreme. An order of magnitude more objects translates to an order of magnitude more risk in any given encounter window. Uncertain whether the Tunguska object was a Taurid swarm member. The circumstantial evidence is substantial. Timing, trajectory, composition, and Boslow's blast wave modeling all point to the Beta Taurid stream. The entry, azimuth, and angle computed from the tree fall pattern at Tunguska are consistent with a Beta Taurid object. The bright nights observed across Europe for several evenings after the event are consistent with a cometary body injecting water vapor and fine dust into the mesosphere at high altitude. But circumstantial evidence, however directionally consistent, is not a confirmed association. It remains a well-supported hypothesis. Lubor Krasak first proposed the Encke connection in 1978. Duncan Steele and Bill Napier reinforced it. Boslow's modeling strengthens it further, but no physical sample was ever recovered from the Tunguska site, and without a sample, the compositional fingerprint that would clinch the identification is missing. Uncertain whether the Younger Dryas boundary event involved a Taurid complex fragment. The evidence is actively debated by competent scientists on both sides, with new papers appearing regularly in both directions. The hypothesis has not been confirmed or conclusively falsified. Uncertain, the composition and physical properties of the larger objects in the Taurid stream. If they are low albedo cometary fragments, surfaces darkened by millennia of solar processing, with reflectivities of 3 to 5%. They will be dramatically harder to detect than rocky asteroids of the same size. A 100-meter cometary fragment at 3% albedo is roughly 10 times fainter than a 100-meter rocky asteroid at 15% albedo. The detection difficulty compounds the uncertainty about population size in a way that makes the absence of detections ambiguous. We might not have found them because they are not there, or we might not have found them because they are too faint for existing surveys. Unknown. The exact density and size distribution of objects in the resonant swarm at sizes above 1 meter. This is the critical gap. Every risk calculation, every probability estimate, every comparison between coherent and stochastic risk models depends on this number, and it has not been directly measured. The 2015 campaign constrained the meteoroid population. Nothing has constrained the asteroid population inside the swarm with comparable rigor. Unknown. Whether NEO Surveyor will be operational and positioned to contribute to the 2032 or 2036 observation campaigns. The telescope is targeting late 2027 launch. Space missions historically experience delays of months to years, and the gap between launch and full operational capability adds additional time. Unknowns. Whether any specific object inside the Taurid Resonant Swarm is on a collision trajectory with Earth in 2032, 2036, or any subsequent encounter. No such object has been identified. No such trajectory has been computed. The concern is entirely about unidentified objects, the ones we have not found, because we have not looked with the right instruments during the right windows with sufficient sensitivity. That last unknown is the whole point. We do not know what is in the swarm at dangerous sizes because we have not adequately looked. The tools now exist to look. The encounter windows are arriving on a schedule that orbital mechanics has fixed. And the only question that matters at this stage of the investigation, is whether we will use those tools during those windows with the intensity and focus the evidence warrants. Part 18, the close I started this investigation with a comet most people have never heard of. A 3.3-year orbit around the Sun. A debris stream older than human civilization. And a question that sits at the intersection of orbital mechanics, planetary defense, and the limits of what we know. Does the wreckage follow rules that our protection framework was not built to handle? I do not have a clean answer. Nobody does. And I think the honesty of that, the admission that the question is genuinely open, that the evidence points in a direction but has not arrived at a destination, that the tools exist but have not been fully deployed, is worth more than false confidence in either direction. What I have, after weeks with this data, is a sense of the weight of the question, and the weight is not in the probability. The probability of a dangerous airburst from the Taurid swarm in any given encounter year is low. I believe that. The data supports it. Boslow says it explicitly. The weight is in the structure of the problem, the combination of clustered risk, predictable timing, and a detection gap that exists because the system was designed for a different kind of threat. The beta Taurids are active right now. You cannot see them. They come from the direction of the Sun, but Earth is passing through the stream this month. Debris is entering the atmosphere as I speak. Most of it is small. Almost all of it burns up without consequence, adding a few micrograms of cometary material to the upper atmosphere in a flash of light that nobody notices against the daytime sky. But the stream contains larger objects. We know this. The 2015 data confirmed it. The question is how large and how many and where inside the resonant corridor. I keep coming back to something Boslow said, and I keep coming back to it because I think it captures, in a single breath, the entire ethical and scientific weight of this investigation. The average probability is extremely low. Even an enhanced risk means the probability would still be low. That is the reassurance. And then, from a risk assessment perspective, we had better check. We had better check. That phrase carries more weight than any individual data point in this investigation, because it comes from a scientist who models airbursts for a living, who co-authored the rebuttal to overblown impact claims, who helped retract a paper that got the physics wrong, who corrected the Younger Dryas impact community on the energetics of atmospheric detonations, who has no professional interest in inflating threats and every professional interest in getting the physics right. When Mark Boslow says we had better check, that is not a man trying to alarm you. That is a man who has looked at the evidence from every angle, weighed the probabilities with more precision than most of us can imagine, assessed the consequences against the cost of looking, and concluded that looking is not optional. I listened to that, and I think you should too. The Vera C. Rubin Observatory is online. Its 8.4 meter mirror and 3.2 gigapixel camera are scanning the sky tonight, the same sky through which the Beta Taurid stream is threading its invisible debris. The full legacy survey of space and time is expected to begin later this year, and when it does, it will scan the entire visible sky every few nights for a decade. The first of Boslow's recommended observation windows, see June 20 to 26, is the window we are in right now, and the telescope has the sensitivity to find objects in the Taurid corridor that no previous instrument on Earth could have detected. If dark, low albedo cometary fragments in the 10 to 100 meter range exist inside the resonant swarm, Rubin has a better chance of finding them than any telescope that has ever operated. If Rubin's survey data from this summer and from the November 2026 nighttime Taurid season reveals new near-Earth objects with orbital elements consistent with the resonant swarm, this story moves fast. We will cover it. If the data comes back clean, no new swarm-associated objects above the meteoroid scale, we will cover that too. Both results change what we know. Both matter. Science does not care which answer we prefer. It cares which answer the data supports. And for the first time in the 30-year history of this debate, the data is about to speak. The 2032 window is 6 years out. By then, the LSST will have accumulated years of data, millions of observations of millions of objects, with the software pipelines to identify moving objects automatically and compute orbits in near real time. EO Surveyor may be operational, scanning the infrared sky for the dark objects that optical telescopes miss. The international planetary defense community will have had time to design, fund, and coordinate the targeted observation campaigns that Boslow has called for. The testing apparatus will either have been deployed or it will not, and we will know more. Not everything, but more. Until then, I will hold the tension honestly. I will not inflate the threat. I will not dismiss it. I will follow the data where it goes and report what it says, including the parts that are uncertain and the parts that are uncomfortable and the parts that do not fit neatly into a headline. If you have watched previous episodes on this channel, the investigations into compound weather events, the deep dives into how institutional assumptions fail under stress, you will recognize the pattern. The most dangerous assumptions are the ones nobody examines, not because they are hidden, not because they are secret, but because they are convenient. The assumption that impact risk is random is convenient. It makes the math clean. It makes the risk manageable, it makes the framework simple, and it may be correct, but it has not been tested against the specific structure in the sky that the evidence says is there. The probability is low, the cost is high, the test is available, and a comet the world forgot existed left behind a river of debris that we cross twice a year, every year, on a schedule older than memory. We will be watching, and when this story moves, we will be here.